All right, let's do something kind of cool. We're going to shrink ourselves down, way, way down to the atomic level. Why? Because we're on a mission to understand something huge. Why stuff behaves the way it does. Why things shatter or bend, or why some things conduct electricity and others, well, don't. We're going to explore the invisible architecture of matter, and it all kicks off with one simple question.
I mean, really think about that for a second. It's a great question, right? They're both these clear, solid things, but you couldn't find two things that act more differently. The answer to that puzzle is hidden deep, deep inside their atomic structure, and that's the exact mystery we are going to solve today. So, to crack this case, we have to start at the very, very beginning. We're going incredibly small, right down to the fundamental building block of literally everything you can see and touch, the atom.
Okay, first things first. Not all atoms of the same element are identical twins. Nope, you've got isotopes. An isotope is still the same element, it has the same number of protons, that's what gives an element its identity, but it's carrying a different number of neutrons. You can kind of think of them as heavier or lighter siblings in the same family.
And that leads us to a really important point that can trip people up. Let's get it straight. The mass number, over on the left, is super simple. It's just a head count, the number of protons and neutrons in one single atom. But the relative atomic mass, on the right, is a totally different beast. It's the weighted average of all the different isotopes of an element based on how common they are in nature. So one's a simple count, the other's an average. Big difference. So we have our atoms, but they're not just floating around in some random jumble. Oh no, they're organized. They're grouped into families that have these surprisingly similar personalities, all laid out for us so beautifully in the periodic table. So let's figure out what makes them tick. So what is the big secret? What's behind these family resemblances? It all boils down to one thing, and it's absolutely crucial: the number of electrons buzzing around in the atom's outermost shell. That's it. That one little detail dictates its entire chemical personality. If elements have the same number of outer electrons, you can bet they're going to act in very similar ways. And here is a perfect example. Let's look at group 1, the alkali metals. As you move down that column on the periodic table, each element gets way more reactive. But why? Well, as you go down, that one lonely outer electron gets farther and farther from the nucleus. It's also shielded by more layers of inner electrons. All this means the nucleus has a weaker and weaker grip on it. And the result? Boom. That electron is way easier to lose, which is what makes a chemical reaction happen. All right, so we know the players, the atoms. Now let's see how they actually connect with each other to build, well, everything. They do this through chemical bonding, and you can really just think of it as atoms having two main relationship styles. First up, we have ionic bonding. I like to call this one the great electron heist. A perfect example is table salt, sodium chloride. The sodium atom is just dying to get rid of its one outer electron, so it loses it and becomes a positive ion. Meanwhile, the chlorine atom greedily snatches up that electron to complete its own outer shell, becoming a negative ion. And what do we know about opposites? They attract. That positive and negative charge pull on each other with this incredibly strong electrostatic force, and that's what holds them together. Now, that whole heist model, it works great for some atoms, but not for everyone. What happens if neither atom wants to give up an electron? What if they're more into cooperating than competing? Is there another way? You bet there is. And that brings us to relationship style number 2, covalent bonding. This isn't a heist, this is a partnership. Here, two non-metal atoms come to an agreement to share a pair of electrons. By sharing, each one gets to feel like it has a full, stable outer shell. It's a total win-win situation. Okay, people, this is it. This is where it all comes together. That choice, to steal an electron or to share it, that isn't some tiny, boring chemical detail. No way. It is everything. That single decision, happening at an invisible atomic level, is what dictates the real, tangible properties we see in our world. It determines if something is a solid, a lipid, or a gas, how easily it melts, and even if it can carry an electric current. And this table just lays out the consequences perfectly. On one side, you've got your ionic compounds. Remember the electron heist? That creates these super powerful forces that lock the ions together in a rigid structure. The result? Hard solids with crazy high melting points. But on the other side, simple covalent compounds, well, they have a very different story. They tend to be gases or liquids with really low melting points. See, the bond type changes the whole game.
So let's dig into that conductivity thing for a second. We know that salt is made of charged particles, right? Positive and negative ions. So here's a little puzzle. Why can't a solid chunk of salt conduct electricity? And the answer is actually pretty simple. Those ions are trapped. They're in jail. In a solid crystal of salt, they are locked into this super rigid structure we call a crystal lattice. They can vibrate a little, sure, but they can't move around. And if your charges can't move, you can't have an electrical current. End of story. So how do we spring them from jail? How do we unleash that electrical potential? You just have to break the lattice. If you crank up the heat and melt the salts, or just dissolve it in some water, those ions are set free. Suddenly, they're mobile, they can move around and carry a charge, and your saltwater solution becomes a fantastic electrical conductor. So what about those simple covalent molecules like iodine? Why are they so easy to melt? Well, here's the key. The covalent bonds inside an iodine molecule are super strong, but the forces that attract one iodine molecule to another iodine molecule, we call those intermolecular forces, are incredibly weak. Think of them like tiny, cheap magnets. It takes almost no energy, just a little bit of heat to break those weak attractions apart, and that's why these things have such low melting and boiling points.
And that brings us full circle, right back to our diamond. Diamond is the ultimate exception, the king of covalent bonds. See, it is held together by sharing electrons, but it's not a bunch of separate molecules with weak forces between them, not at all. Instead, every single carbon atom is covalently bonded to 4 other carbon atoms, which are bonded to 4 others, and on and on and on. It creates one single, giant, interconnected molecule. To break a diamond, you're not just overcoming some weak little forces. You have to physically break these super strong covalent bonds themselves. And that is the secret to its incredible, legendary hardness.
Okay, so we've seen how the type of bond creates the properties of a substance. Now let's wrap up by quickly looking at how these bonded particles arrange themselves and how we can tell the difference between them and things that are just kind of mixed together. You know, the states of matter are really just a big battle between the forces holding particles together and the energy trying to tear them apart. In a liquid, the particles have enough energy to break out of fixed positions and slide past each other, but not enough to escape completely. But if you pump in more energy, poof, you get a gas, where the particles break free entirely and just fly all over the place. And this is another one of those super important ideas. In a compound, like H2O, water, the elements are chemically bonded together in a fixed ratio, always 2 hydrogens to 1 oxygen. You can only break them apart with another chemical reaction. But in a mixture, say salt and sand, the parts are just physically jumbled up. You can have any ratio you want, and you can separate them using simple physical methods, no chemistry required. Speaking of physical separation, chromatography is such a cool example. You put a drop of ink on some paper, and as a solvent moves up the paper, it drags the different colored dyes along with it, but at different speeds. By calculating this thing called the RF value, which is just a ratio of how far a dye traveled versus how far the solvent traveled, we can create a unique fingerprint for that substance. It's like chemical detective work. Diffusion is another great example. Imagine you have some ammonia gas at one end of a tube and some hydrogen chloride gas at the other. They're both going to start spreading out. But here's the thing. The ammonia molecules are lighter, so they move faster. That means when the 2 gases finally meet and react to form that little white ring you see, it always forms closer to the side where the heavier, slower hydrogen chloride started. Pretty neat, huh? So there you have it. From the type of bond between atoms to the way particles arrange themselves, these invisible rules define our entire physical world. The hardness of a diamond, the way ice melts in your hand, it all comes back to a simple choice at the atomic level. Do we steal or do we share? So the next time you pick something up, just look at it for a second. Ask yourself, what invisible story is this thing telling me?